Section 9.7 covers resonance and formal charge. In a previous video we looked at resonance. This time we're going to look at formal charge. There's an equation in your book for formal charge that we'll be using, and here I'm going to use one of the same molecules that we used a previous time, diazomethane, which has two resonance forms. So this will give us a lot of atoms for which to calculate the formal charge. To calculate formal charge, first we look at the valence electrons. That's how many electrons the free atom has just by itself in this, if it were alone and neutral. Then we look at what does the atom have in the molecule, in the structure. And there's two ways that we see electrons in the structure. Non-bonding electrons, those are the dots, or the unshared electrons. And we have bonding electrons, those are the lines, the shared electrons. If they're being shared between two atoms, each atom only gets half of them when they divvy them up for formal charge. So let's go ahead and calculate the formal charge for one of these atoms. And here I'll highlight this N in green, and we'll calculate the formal charge on this atom. In terms of how many valence electrons the free atom has, nitrogen would have 5 if it were by itself. Then we subtract what it has in the molecule. Non-bonding dots, this nitrogen in green has 2 dots, so we're going to subtract those. Bonding, the lines, it's sharing 2, 4, 6, so we take half of the 6 that it's sharing. That's 5 that it would have by itself, minus 2 plus 3 that it has in the structure. 5 minus 5 gives us a 0 formal charge for that nitrogen in green. Now let's try another atom. Let's try this nitrogen in red. In terms of valence electrons, nitrogen by itself would have 5. So now we'll subtract what it has in the atom, in the structure. Non-bonding electrons, dots. This red N has no dots, no unshared electrons. Bonding electrons, it has a full 8 that it's sharing, 2, 4, 6, 8 from those 4 bonds, but we only take half of those 8, half of the shared, so that's 5 minus 4, and that leaves us with a +1 formal charge on this nitrogen. If it's used to having 5 negative electrons in its valence shell and it only has 4, that's 1 fewer negative, leaving behind a positive. Now we can move over to the next atom, this carbon that I've highlighted in blue. To calculate its formal charge, it would have 4 valence electrons if it were by itself. It has 2 non-bonding, 2 dots. And if we take half of the bonding, the lines represent 2, 4, 6. So half of those 6. 4 that it would have by itself. 2 and 3 that it has in the structure. 4 minus 5 is minus 1. The formal charge on that carbon is -1. Finally, we can move to one of the hydrogens, and the formal charge on hydrogen, it's used to having just 1 valence electron. In the structure, in terms of non-bonding electrons, there are no dots around this H, so that's 0. So we're going to take half of the bonding, and it's sharing 2, so half of 2, that's 1 minus 1, or 0. So the formal charge on this H is 0. The other H also has no dots and 1 bond, so the calculation would be the same. It would be 0 as well. Now we're going to calculate the formal charges of the atoms in this other resonance form. Since the electrons are distributed differently in resonance forms, the formal charges for some of them will be different. Now, instead of doing it the way we did before, I'm still going to use the formula, but I'm going to do it in more of a visual manner. And I'm going to highlight each electron by emphasizing it in black. The dots are fairly obvious. Remember, each line is 2 electrons. 1, 2, 1, 2, 1, 2, 1, 2. By doing this, we should be able to more visually see which electrons are going to be assigned to which atoms. So if we looked at the formal charge on one of the nitrogens, nitrogen normally has 5 when it's by itself. If we circle this nitrogen, it's more easy to split the shared electrons in half and see how many it has in the structure. And it looks like this N has 1, 2, 3, 4, 5, 6 in the structure. A -1 formal charge. Next, if we calculate the formal charge of the other nitrogen, nitrogen always has 5 when it's by itself. Circling this one, it looks like it has 1, 2, 3, 4 around it. 5 minus 4 is going to give me +1. That nitrogen has +1. 4 around it is fewer than the 5 negatives it's used to. Fewer negatives means you're left behind with a positive. Next, we look at the formal charge on the carbon. Carbon, when it's by itself, has 4 valence electrons. If we circle the dots that are immediately next door to that carbon, it has 1, 2, 3, 4 dots in the structure. 4 minus 4 is 0, so the formal charge on that carbon would be 0, because in the structure it kind of looks like it has the same number that it's used to having. Finally, we could look at the formal charge on each hydrogen. Hydrogen is accustomed to having 1. If we circle it here, it looks like it only has 1 in its immediate vicinity, so that formal charge is 0. Both hydrogens have 0 formal charges. Now, I've cleaned this up a little bit and taken away some of the color to point out one other thing. These structures are not equivalent. It turns out that for formal charges, 0 formal charge is best. That means the atom has the same number of electrons that what it's used to having, so it's going to be very stable. Another way to say stable is low in energy, which is good. Things like to roll downhill, low energy. So if zeros are best, let's focus on where the non-zeros are located. And we'll go ahead and get rid of the zeros, the good things, and focus on what's bad. So you might notice the nitrogen in the middle has a +1 in this structure. It's also +1 in that structure. That's not too different. That same N has a +1. But if we look at where the -1 is located, this one has a -1 on an N. This one has a -1 on a C. So what's better, a -1 on an N or a -1 on a C? If we think about electronegativity, on the periodic table, carbon is about here and nitrogen is about there. Things get more electronegative as you move to the right, so N is more electronegative than carbon. Remember, electronegativity is how much you pull electrons to yourself. If you pull electrons to yourself, that means you like to be negative. So N is better with a negative charge. So this structure on the right is going to be better, and this structure on the left is going to be worse. Another way to say better is, of course, more stable, or lower in energy. And if it's more stable, that means that these aren't going to contribute 50-50 to the resonance hybrid. The resonance hybrid, the real molecule, is going to look more like the more stable one. So the real molecule looks more like this one and less like the other one on the left. One last thing to note about these structures: if you add up all the charges, the net charge on the whole thing, since there's no charge listed, should be 0. A +1 and a -1 add up to 0. A -1 and a +1 add up to 0. Your individual charges on each atom should give you the net charge on the whole thing. So if your whole thing were +3, your individual formal charges should add up to be +3. There are lots more examples in your book. Keep practicing away.